Functions are so commonly studied across mathematics that there are many important properties which are defined that a function may or may not have. In this video we're going to investigate a few of those important properties that apply to general functions. I'm going to begin with a definition of something associated to every function, which is the image of a function. So the definition is like this. You take a function f with domain x and with codomain y, and then the image of f, which we write like this, is defined to be the set of all things f of x for x in the domain of f. Now you will notice what's going on here, that this is a subset of something. This is a subset of the codomain y. So let's just look at a quick example of what's going on here. Let's take, for example, f from the real numbers to the real numbers. So the codomain of f and the domain of f are both the set of real numbers, and the rule is equal to f of x is equal to x squared. Alright, so the image of f is the set of all things x squared for a real number x. And you know which real numbers are squares. So a number is equal to the square of the real number if and only if it's not negative. So this is all x. Let's write this in a slightly less confusing way, or y, such that y is greater than or equal to 0. Those are the numbers which are equal to the square of a real number. So in analysis you would write this using interval notation. You'd write this as something like 0 to infinity, the half-open interval from 0 to infinity, meaning all the non-negative real numbers. So you'll notice that this is a proper subset of the codomain of f. So im f, in this case, is a proper subset of the codomain of f. So in general, the image of a function is a subset of the codomain, but it need not be all of the codomain. And again, this is an important point to get right. It's another common source of confusion, so we deserve the danger symbol for this one. The danger symbol is to remind you that the codomain of a function and the image of a function are not the same in general. Oops. Image of f is always a subset of the codomain of f. But it may not equal the codomain. As this example shows. So sometimes people make this even more confusing by introducing a third concept, which is, or a third piece of vocabulary, a third word, which is the range of a function. Sometimes you will see people talk about the range. And what makes it even more confusing is when some people talk about the range, they mean the codomain, and some other people, when they talk about the range, they mean the image. So this is so confusing that we will never use the word range in Math 5. We will use image when we want to talk about the image, and we will use the word codomain when we want to talk about the codomain. And it's important to remember that the image is always a subset of the codomain, but it might not be equal to the codomain. It could be a proper subset of the codomain, as this example shows. So we're now ready to define the three most important function properties, and they're so important, they're so common that they have two different names, or at least two of them have two different names. So let's begin with a function f whose domain is x and whose codomain is y. We then say f is injective, or one-to-one, to mean that for every a and b in the domain of f, if f of a is equal to f of b, then actually a must be equal to b. So the contrapositive of that would be to say that if A is not equal to B, then f of A is not equal to f of B. Next definition is called surjectivity, or being onto. So a function is surjective or onto if for every element in the codomain, every y in the codomain, there is at least one element in the domain such that f sends that element of the domain to this given element of the codomain. So you could rephrase this by saying equivalently, f is surjective if and only if the image of f is equal to y. So you can see that there is a special name for functions whose codomain is equal to their image. That is surjective or onto. And finally, we say a function is a bijection if and only if it's both injective and surjective. So this is a lot of definitions. Let's look at some examples to illustrate these definitions. So if I take, to begin with, the function f, whose domain is the real numbers and whose codomain is the real numbers, defined by f of x is equal to x squared, then this function is not injective. And the reason that it's not injective is that there are two different elements of the domain which have the same image under f. So f sends two different things to the same place. So for example, f of 1 is equal to f of minus 1 because they're both equal to 1. So f is not injective. Okay, let's try now a different example. So we'll return to this one on the next slide, but for the moment let's think of a different one. So let's take a function g from the natural numbers to the natural numbers. Let's think about this one. So g of n is going to be defined to be n plus 1. Now this function is injective. And the reason for that is that if you have two things whose image under g is equal, so if g of a equals g of b, then, well, a plus 1 is equal to b plus 1. So you can just subtract 1 from both sides. So a is equal to b. All right, so g fulfills the definition of being injective. If g of a is equal to g of b for any a and b in the domain of g, then actually a must be equal to b. On the other hand, g is not surjective. So not onto, not surjective. Can you think why it's not onto? So being onto means that the image of g is equal to the natural numbers, but the image of g is not the natural numbers. So remember, in Math 5, the natural numbers consist of 1 and 2, 0 and 1 and 2 and so on. But the image of g does not contain 1, because if you do g to something, you add 1 to it. So the image of g is a proper subset of the codomain. It's not equal to anything to the whole codomain. In particular, there is an element, namely 0, which is in the codomain and which is not in the image. So g is not onto. Let's look at one final example then. Let's look at h, where h is going to go from the integers to the integers, and h is going to have the same rule as g did. So h of n is equal to n plus 1. So this function is injective for the same reason as g was injective. You could do exactly the same argument, but this time h is surjective, or onto. And the reason for that is if you take any element in the codomain, so let's say z is in the codomain, little z is in the codomain, z is equal to h of z minus 1. Z minus 1 is a legitimate member of the domain of H, and so this shows that every element of the codomain is actually in the image. So let me put this in a more straightforward way. So the image of H equals Z. We've shown every element of the codomain is actually in the image as well. So you might think, well, why doesn't that same argument prove that G is onto? Well, maybe pause the video and think about that. Why can't I do the same argument to prove that G is onto? And the answer is that the argument almost works, but it doesn't quite work. Because if you chose 0 as your Z, then 0 minus 1 is not a natural number, right? Minus 1 isn't a natural number. So this argument wouldn't work because it wouldn't show that every element of the codomain was also in the image. You can't show that 0 is in the image of G this way because minus 1 is not a natural number. So you have to pay careful attention not just to the definition of the rule, but to what is the domain and what is the codomain when you're thinking about function properties, as this example of G and H makes clear. So because these are tricky concepts to work with, let's look at some more examples where we're going to try and determine whether or not some functions are injective and surjective and bijective. And this time I'm going to have 4 functions all with the same rule, but with different domains and codomains, beginning with f from the real numbers to the real numbers, whose rule is f of x is equal to x squared. So is this injective? Pause the video, answer the question. Right, no, this is not injective. For example, f of minus 1 is equal to f of 1, so f is sending 2 different things to the same place, so it is not injective. All right, is it surjective? Again, pause the video and think for yourself. Okay, so the answer is, well, minus 1 is not in the image of f. There is no real number whose square is equal to minus 1. So, no, right? The image is not equal to the codomain because there is no real number whose square is minus 1, so this function is not surjective. And of course, to be bijective, you've got to be injective and surjective, and this isn't either, so the answer here is no again. Okay, let's move on to the next row of my table of examples where we have a function g whose domain is the real numbers and whose codomain is the interval which is closed at 0 and open at infinity. So that means all of the non-negative real numbers. This is the kind of notation that you would see in analysis. And the rule for g is again that g of x is equal to x squared. So this time g is again not injective, right? Exactly the same reason. G of minus 1 is equal to g of 1, or g of minus 2 is equal to 2, or whatever. So no, it is not injective. On the other hand, this time g is surjective, because if you've got an element of the codomain of g, then it is a non-negative real number, so it's got a square root. So let's write this down. If y is in 0 infinity, then root y is a genuine real number, and g of root y is equal to y again. Okay, this only works because y was a non-negative real number. Right? Our argument wouldn't work for f because for f the codomain had negative numbers which don't have real square roots. But in this case, the codomain consists of non-negative real numbers. Every non-negative real number has a real square root. So yes, this function is surjective because for every element of the codomain you can find something which g sends to that particular element. So this is a surjective function. The image is equal to the codomain. Okay, but it's still not bijective because to be bijective you've got to be injective and surjective, and this one wasn't injective. Okay, let's look at this function h. So h now has domain, the set of non-negative real numbers, so the half-open interval closed at 0 and open at infinity. and its codomain is the real numbers. So this time, is it injective? What do you think? Pause the video, think about the answer. Okay, well, this time the answer is yes, it is injective, because the only way that the squaring function fails to be injective is because it sends minus x to x for any x. But this time our domain doesn't contain two different numbers x and minus x, because the domain only has non-negative entries, non-negative elements. So this time the function is injective because you cannot find two different non-negative numbers with the same square. Okay, is it surjective? Of course, the answer is no, right? The answer is no for the same reason that f was not surjective. So, right, same reason up here. And of course, it is also not bijective, because to be bijective, you've got to be injective and surjective. This one isn't surjective. Okay, last example then. This time we have a function k, whose domain is all the non-positive real numbers. So all the real numbers which are less than or equal to 0. And its codomain is all the non-negative real numbers. So all the real numbers which are greater than or equal to 0. And yet again, the rule is that k of x is equal to x squared. So is it injective? Okay, the answer is yes, it is injective, right? And the answer is injective because, well, basically the same reason that h was injective. So sort of the same reason as here. Okay, is it surjective? Okay, the answer is yes, it is surjective. And again, the reason it's surjective is similar to the reason that g was surjective. You can find, if you have any non-negative real number, then it's got a negative square root. So if you've got a non-negative real number y, so an element of the codomain of k called y, then minus the square root of y is an element of this thing, and k sends minus the square root of y to y. So every element of the codomain is actually in the image, and that means this thing is surjective. Okay, so this one is injective and surjective, and therefore it is bijective. So we have a bijective function from the non-positive real numbers to the non-negative real numbers. And that's our four examples where the rule was the same, but the properties were different every time. So I hope I've made this really clear that when you're thinking about function properties, injectivity, surjectivity, and bijectivity, you can't just think about the rule, you've got to think about the domain and the codomain as well. Okay, final example. So, well, final property or final connection between things that we've thought about already and function properties. And that is a connection between the idea of a bijection and the idea of the size of two sets. And in particular, we're going to think about how bijections between two sets are related to those two sets having the same size or the same cardinality. So I'd like you to imagine a terrible monster, and to help your imagination, I've drawn a picture of a terrible monster on this slide. A terrible monster with thousands of hands, in fact millions of hands, in fact so many hands that you can't count how many hands it has. And in each of these uncountable number of hands is a person which the monster is going to eat. Now, there are so many hands that you can't count them. But what you do know is that in each hand, every hand, it holds a human, one human in every hand. So what you know is that the number of hands, whatever it is the same as the number of people. And the reason for that is that you compare them up, right? Each hand is holding exactly one human. So the number of hands this monster has is exactly the same as the number of humans that it's holding, even though there are so many of those things that we can't count them. So another way to think about this pairing up between hands and people is to think that there is a bijection. There is a bijection between the set of the monster's hands and the set of people, which sends a hand to the person that it's holding. So that function, which sends a hand to the person it is holding, is 1-to-1, because there are no two hands holding the same person, right? Each hand has its own person. And it's onto, because every person that the monster is holding is being held by one of its hands. So, in conclusion, we can think of the fact that these two sets, set of hands and the set of people, has the same size, as being witnessed by the fact that there is a bijection between those two sets, the set of hands and the set of people. And we can use this to give a definition of two sets having the same size, which is useful not only for finite sets, where we already have a good definition for the size of a set because we can just count the elements, but that works for infinite sets as well. So two sets have the same size or the same cardinality if and only if. So let me give these sets a name. So let's say X and Y. They have the same size if and only if there is a bijection from X to Y. Now that is a very useful idea to have because it lets us use our knowledge of functions to count things. In particular, if you want to show that two sets have got the same size, then all you need to do is come up with a bijection between those two sets, and you've established that they do have the same size. This is very useful when you're trying to do counting proofs, or you're trying to work out how many things something has, or you're trying to show that two sets have the same size. You can do it by finding a bijection between them.